So I'm Sumanth. I work here as an engineer in analytics team in Apigee. So we have some experience to share with Spark and how we basically aggregate the data that what we
Louder, little bit louder.
To be louder?
A little louder.
Okay. So I'm Sumanth. I work here as engineer in Apigee. I work in crunching numbers, basically in analytics and aggregating data. We do quite a lot of stuff about we collect tons and tons of data, and let me just go over how do we collect the data, what are some of the use cases, and how we have basically used Spark to basically do a very simple aggregation, and how it really differs from MapReduce. Right? I'm not going to deep into the how it is like every single bit, how it is different, and what are some of the learnings that what we have got from using Spark. Right? So those are some of the things. So I have very little set of slides. I have also a small demo on how to really, run it, or basically what we run the same program in production. So that's what I'm going to just talk about. So some of the use cases, just before going over all the use cases, let's see how do we really get all the data that what we want to really crunch. Basically, Apigee is an API company. We have an API platform where we have billions and billions of APIs that goes in. It basically gives you a gateway to the business to really have digital presence, so that others can really interact through our API platform, the businesses at the back end. Quite simple. And as the data goes through our cloud platform, or basically the API platform, we generate tons and tons of data. A very simple thing may be something like location data from where the users are trying to make a call. Let's take something like Big Bazaar or someone who really wants, someone is buying through our platform, and we also collect data in between. Just we are sitting in between and just have tons and tons of data. So the data looks something like HTTP response, as you would look into some of the Apache server logs. How many have really seen Apache access logs? So you all have come across, right? You have tons of data where the IP originates and stuff like that. Similarly, when someone makes a call through our API platform, we also collect the data which is similar, but also it is pretty much enriched. So what is the value of all this data? You have all the server data. What is the value that you can gain about?
Just to understand, if someone is doing some sort of attack on my system, or like someone is creating the content, or like what is the user behavior?
Oh, that's one of the things. Quite simple thing is that I really, for Big Bazaar, I really want to know from which cities people are buying, or even for Flipkart or someone, right? So you have an IP data, you can really get from where they are trying to get, or some of the most advanced use cases may be something like which devices people are really using to use it. So that way I can decide whether I want to really go for a tablet or iPhone or something like that. So there are various things that you can really infer from the data. But before that, you really need to store and process the data, right? We have a data warehouse where we store the data. Now the biggest thing is about processing data. One of the fundamental things about processing data is all about aggregations, and that's what I'm going to speak, and how Spark really fits in our frame of things. Where how can we basically aggregate the data. So the use cases are quite simple. Summarize or aggregate the data over different dimensions. So in the Apache server now, what could be the different dimensions?
Browser, IP.
Yeah, browser, IP, whatever. Right? The user agent is a huge thing which has lots and lots of dimensions, and given a terabytes of data, you need to probably be able to go over it. And in our case, we are heavily multi-tenanted. Right? We support tons and many customers, and the customer ranges from different sizes. Like one of the biggest customers may be running something like thousands of TPS. Some of the smallest customers may be running some tens of TPS. So we have at any point in time large data sets which can run to several gigabytes where we want to really aggregate, and there are data sets which quite small in number, like KBs and ABs. So now we need a platform, basically a compute engine, which can really adhere to this, one of the fundamental things. You just cannot put some huge crunching platform like Hadoop or something, which has got a huge startup time.
So we haven't really looked at Apigee with detail, but if I understand, you only look at Apache server logs. Is that the only data source?
No, we don't look into Apache server logs as such. The data is similar to Apache server logs, but we ourselves generate so much of data when an API call is made through our platform.
So
right?
API calls are more or less integrating with e-commerce websites.
It can be literally anything. It can be retail. It can be, any such thing. We provide the API platforms.
When it comes to log, do you then structure it or you take as a structure?
No, we don't have a log file as such. It's just a similarity between the log file. We don't collect it through log file. When an API call is made through our platform, we have a different kind of a tag. we collect all the data that is required from
That is structured.
it is semi-structured. It is semi-structured. It is not. We have a set of things which are which are pretty well known. We can really define it, and the customers can really define their own fields. Very simple example maybe that someone wants to really compute a revenue out of whatever the API that they may be making, right? So they can add a new field. It's called custom variables. Nothing, right? And they can say that okay, now we want to aggregate on this particular field. So they can add these custom variables. They can add, but there are certain standard fields. What is the response code or something? Is a response field? What is the IP that we see? Is a standard field. So it's somewhat a semi-structured. We have all kinds of data types for it. But certainly it is not unstructured. That's why we are saying. So the use cases here are so the use cases are quite simple. We want to summarize and aggregate over large data sets and smaller data sets also with equal efficiency. You just cannot put a huge engine which will take some like a distributed engine which will have some 20 nodes and you just put some MBs of data. It's just waste of time. So we need a different way of doing it. And the other thing is that we can have time granularity of the aggregates where you do minutely aggregations of the data. You want to do with the same processing engine or the same code. You would want to do something like daily aggregation or hourly aggregation, maybe something like a roll-up or something like that. And given various kinds of data, we have various kinds of aggregates that is over a single data set. One of the examples may be something like you have it based on something like IP address or something like a city information. What is the data? I want to do one kind of an aggregation. Or we have something like APIs that people use, right? So we want to, based on the APIs, we really want to do an aggregation. That is one thing. And there are multiple things. And the other thing is that every day we might get newer and newer APIs. People want different set of APIs. So ultimately this comes down to that your solution has to be extensible in such a way that it is very easy for you to add another aggregation. So it makes it a somewhat a framework that you develop on top of a computing engine that you can easily use. That's what it's all about. And the last point is something like we don't want to do lots of IOs. Like you just don't want to spend so much of time doing IOs. So that you want to load something data in memory or somewhere and do all the aggregations in one shot. That's something which is very useful. So we have picked Spark because of its nature, which of the generality that it provides. One of the generality that it provides is the ability to process small files, big files in a much more efficient way compared to the other computing platforms. So that's what we have picked Spark. And this is a very basic thing of how do you really aggregate. Even it's there, but I really want to hear from you. How do you want to really kind of aggregate? It's quite simple actually. Because I can write a small data set and then you yourself can just come over and then say that it's quite simple to aggregate it. So let's say that we have an API which is something like city mapper or something like item is on API and there is some IP client IP 10.1.2 and something and the revenue is something like $300, something like this. And I want to aggregate on these things. And then there are so many such API calls that is going through from different customers like that, and this generates $200 or something like that. So how do you now aggregate? It's a very simple thing. This data set will be huge. It will be in gigabytes.
Take a field, make it as a key, and
simple, right?
Reduce by.
Yeah, exactly. Reduce by. So, but do you really want to store all of them? Let's say I want to make API to something like what is this client IP or something like that. So, if you want to store all these things in memory, right, it's pretty costly. And as the fields and the dimensions go higher, it becomes it becomes really costly. So, what we have done is a quite simple thing. We just don't store all the things in memory. We make a hash out of it and use the keys consistently and store this information elsewhere. So that way we are not storing the entire data set. We can just store the keys, use those keys and then just reduce it like you said, right? Simple. So we have dimensions from which we make the keys, simple, and make the hash out of the keys so that it is more efficient. And then what we do is that we basically apply the reduce to really on the set of metrics to really get it. And some of the reduce operations or the operators, that is nothing but we have some min, max, average, and we have also certain tough ones to compute, which are quantiles, or what is called as percentiles. Right? That's some of the things. So now I'm going to just speak about how do we really done it using Spark. So this is about why we have really picked Spark. Like I said, it was basically to use the generality because it can really process the KBs, the MBs and the GBs very efficiently. Right? And Spark is so well designed and so modular that it can be run in local mode. I'm going to show how to run it on my laptop. Same program, almost identical, can be run in a huge distributed cluster. I mean, you don't have to change a lot of code there, right? So that's why we have really picked Spark. And the other thing is that we have given this higher level of abstractions. Probably you are familiar with the map and the reduced things that's available. We can use the same setup, just define what you want. We have what is known as conditional mapping. If the IP address is this, you really want to then do a different kind of aggregates. And if the IP address is something else, you really want to do something else. So this is known as conditional mapping or conditional reduction. This, someone might have a question, why you probably have not used something like Spark SQL, load all the data to RDB. It becomes very difficult to do this conditional items. If this field is null, then you want to handle this differently, the aggregation that you want to generate. If this field is not null. Actually, null and not null is a pretty simple thing that can be done in SQLs, but if you have complex conditional things, it becomes a little difficult to write SQLs. Right? That's why we have taken the other approach of writing the code ourselves using this map. Yes.
Yeah. So is it conditional map means that rdt.map is inside some Scala or Java?
Yeah, it is actually in Java.
Okay.
I'll show the code also.
Okay.
I have literally written a mapper and a reducer class. Of course, it is nothing similar to HDFS. It is just a function. I have extended the function and the code is in Java. Okay. So that's how we have written. So going back to the use cases, so Spark handles the generality. Spark is quite fast when compared to Hadoop because of the low data cost. And the most important thing is that Spark can be locally and embedded. This has got a great advantage when you have a huge box and you don't need all these fancy things of fault. Obviously, you need fault tolerance and all. But if you are generating something like a megabytes file and you want to do it locally, then you are pretty well enough. So that we can do very fast. So our solution is quite simple. We have a metadata driven framework where you define a set of what do you call it as the aggregation schema. Basically, you define the dimensions, you define the metrics in a particular JSON format, and there is a framework that what we have developed on Spark, which can really take that as input and then over RDD it can really operate on and then just get the result. So let me just show you how the real metadata file really looks like. So, sorry, Steam. Yeah. Now can you see?
Can you say view presentation mode?
View presentation. Mine might be old, not sure.
Yeah, yeah.
Okay, that's good.
Yeah.
So basically our metadata, basically this is nothing but an input to our framework, which actually contains what are the fields that we want to aggregate on. Like API proxy is, like I said, some like by item or something like that, and then there's the API product. And these are some of the things like city, country, continent, and types. So this is the basic input on the dimensions, and this is the set of metrics that you would want to really be able to generate. Very simple thing is that a message count, given all these dimensions, how many messages or the events have gone through our API is one of the things that I really want to cover. And the response time and many other things. So if you really see, this supports something like derived metrics, where you derive a particular metric, like something like what was the data exchange in a particular API request and response, using the request size and the response size. So, and the other one may be something like applying a function at runtime, given a set of dimension metrics, you really want to apply a function. So we have support even for that. Apply function, check-in range, if it is in particular range for the response code, 300, 400. We can compute what is the error or something. So you can extend these functions and then really extend the framework. That's how this will be. So this is about a simple framework that input to the framework. That's what we have. So, go back slides. Any questions till now? Anything that you would want to know about Spark and why we have picked Spark or something like that?
You said like you are using Java for Spark, right?
Yeah.
So how is your experience when generally people whenever they say a Spark, right? They
Yes.
recommend Scala.
Yes.
So like as you are working with Java and Spark, like what is your feedback or what is your
I have not seen much of difference. I have worked in the Scala. Scala is very easy, succinct to develop and all.
Okay.
Just pick it Java here because it's pretty easy to compile, to integrate with our existing code. It doesn't make a lot of difference that I have also. Not a lot of difference. Actually, Scala it's much easier to write. You will write the same program that I have written, probably 30 lines of code.
But I think if you use Spark.stats and Amlet, it will be much easier than writing program in Java. So then you're using functionality of Spark and Scala.
Sorry,
Instead of writing codes in Java, if you use
Yes.
Amlib and stats functionality of Spark and Scala, I think it will be much easier than this. You can create your any variable on the fly and do the calculations. You don't have to write even the codes for it.
So the basic flow is quite simple. You have defined your aggregation schema, and this also fits into one of the use cases where we want to really create. We want to make the framework extensible. Now, let's say tomorrow I want to create another aggregate that is required. Just create that schema file and you are done. Basically, know the data types and stuff like that, and you are done. So just feed the files and the schema. It just gives you the output, and you can also define a result format. Let's say you want to do it in CSV format. You can also do it in CSV. That's how it really works. The best part is that it works in almost the same, except for one small change. It works in local mode or distributed mode. And the other bigger advantage is that since Spark does the memory management so well that you can literally load a gigabits of file and then still allow everything to be in memory and just make a single pass over the data and get all the things that you want, basically the aggregates. So our framework really supports min, max, and quantiles and stuff like that. Right? We have a few phases, we have a map phase where we do a schema discovery. Let's say schema, the input file may be a CSV file. If it's JSON, we don't have to do much. Or an Avro file, we don't have to do much because the schema is quite embedded. But let's say it's a CSV file or a gzip CSV file or something like that. What we do is basically schema discovery and then just generate the map. The map is generated using some kind of a hash function. It's nothing but an RDD. And then just after that, it's nothing but a reduce function. So I want to specifically talk about the reduce functions using digest. The other reduce functions are mostly memoryless. Like you have some min, max. Some you don't have to have anything data points in memory. You don't have to have data points in memory if you really want to compute min max, right? You just have to have one data point for that particular particular partition, just a min. And they are all associative and commutative operations. You will be able to find it out. But quantal computations is quite complex. Let's say you have terabytes of data and you really want the distribution of data. In our case, we know the distribution of data, and the quantals computation is pretty easy using digests. So the digests are quite simple that you don't keep all the data points. Basically keep the data points in intervals and then compute the quantals. Obviously it's an approximation, and if you really know the data distribution, you can really compute the quantals in pretty decent error bars. So that's what we do to save quite a lot of time instead of keeping all the data points in memory computed. Obviously the last phase is somewhat a results collection. You might have worked in a distributed setup and you want to really collect all the files and just get all the results formatted and many other things, because the results will be ultimately in part files, right? We want to get the results and then upload it to somewhere else. So that's what we do in the results collection phase.
One question.
Yes?
Yeah, so in the schema discovery, are you doing it manually for JSON and Avro, or are you using data source API, which is there in Spark now?
We use not the data source, we are doing it somewhat manually. We are little work, we are in 1.1 kind of.
Okay.
Not yet reaching. Yeah.
Here's some question. I think this whole process is a pipeline process, right? So have you guys looked at using pipeline RD
No, nothing.
Not really.
Not it. We are not it.
But do you have your own pipeline, data flow framework, something like that?
We don't have a data flow framework. Actually, this aggregate driver, it's called as an aggregate driver. It actually fits into a larger architecture, which.
So I understand the aggregation part. I thought what you alluded to is, let's say you get a zip file,
Yes.
right? And inside you have, let's say, a bunch of CSVs and JSONs and all that.
Yes.
The whole idea is that you should be able to interpret or infer the metadata all the way down and then convert it to something which is aggregated. Right?
Yes.
So before you come to aggregation stage, how do you create this dynamic flow or data flow? Is it something?
Yeah, I will
something
explain
about
it.
data flow and all that.
Yeah.
So,
Because we have a different framework. This is one part. We have a completely different mechanism to. I'll just show it once. Let me go over this. I'll just show that in a bit on how it really fits into our very larger architecture of computing aggregates. Or for that matter, you can literally compute anything with it. And there is a Spark cluster which is running, and then you just can feed data to get back the results. And how do you maintain some kind of what do you call it as? I'm not getting exactly one's processing semantics. You put a file, you really compute it, and you crashed. Right? And how do you really say that it crashed? There is a task manager that is sitting. I'll just speak a little bit about it. So it's little specific to our own architecture. So this is more generic. This driver can be taken, put the files, put the schema. I'll just show that, and then I'll move on to how it really fits into our picture. So this is some of the results. Like I was saying, it can really process the files with equal efficiency. You take a 500 KB file, just process in 1 second. There is hardly any startup cost associated with a Spark context or anything. And then you take something like a 445 MB, which actually expands to something like 4 gigs or something like in 2 gigs or something like that. You can really nearly compute that in something like 170 seconds or something flat. That's the results. And one of the key takeaway from this results is it is linearly scalable, both scale up as well as scale out, right? So what linearly scalable really means is you literally have, let's say you have a 32 core and a 64 gigs box, and you put Spark and this framework, and you have give it feed, it just half the time. That's what we have really seen. That's what it really means. You increase the file input as well as your whatever the processing power, it actually gives you the same times. So it is purely linearly scalable. That is one thing we have established in our experience. So these are some of any questions till now. Any questions? I mean, it's quite simple. It's not any. But if you still have any questions about Spark or anything in general, how we have or why we have decided or something.
there's one more question there. If you hit, I mean, see, while I look at Spark, I also say that hey, how many have hit maybe the limits of terabit? Have you guys in your data sets experienced, crossing the limits beyond?
We are not at
let's say
hit
what
terabytes.
People claim Spark is made.
No, we are not at hit terabytes.
Okay.
We have hit several hundred gigabytes, and that is in experimental state. In production, we are not at hit even hundreds of terabytes or like hundreds of gigabytes also we are not hit. We have certainly tested it locally. Not yet. So some of the learnings that what we had is that I initially was over enthusiastic to do lots of parallelization. I mean, it's actually a dampener. You just don't do so much of parallelization. So you just do whatever is required. Like you have n cores, max you can just go to 2x cores. That is one thing that what we have done. And the second thing is that Spark generates tons and tons of objects. So if you are really tuning, the one thing that you would really want to tune is the GC. And parallel GC, at least we were using Java 7. I don't know about Java 8, I have not done any experiments on Java 8. Use a pretty decent parallel GC, but obviously tune the new ratio as per your requirements. Okay. And this one was the initial days. I think that is also well documented. The group by key is pretty costlier. Instead, use a map, generate your own map, and then just use reduce by key. It is very, very efficient compared to group by key and then aggregate by key. Then the last thing is that you can use memory only. It does all the management. It has got different storage levels like memory only, memory and disk and stuff like that. You don't have to really use all of them. Just use memory only. So what it really means is that if something is knocked out of memory, it is very easy for Spark to recompute it than storing every single bit of information in disk as well as in memory. Of course, this can be changed. If you are constantly recomputing, then the cost is more. In our case, it never happens. So using memory only has got a tremendous effect. So that's all I had. To answer your question, how it really fits in and larger architecture and so this is our different architecture, of course, somewhat confidential. So just that here is the exact Spark aggregator and driver which is sitting, and we upload it to a message queue. That the file is available. We basically put the data into S3 and we say that okay, the file is available in S3, now go and compute. So there is a task manager which is sitting, which picks up this notification that the files are available and then just starts the process. And once the results are finished, we also want to load it back to the query store. Basically we have a query serving store. The results are available from the compute cluster, and then from there you really want to be able to upload back the data. Again, it's done by a notification system.
What I can interpret what you're saying is, let's say if I had two different kind of pipelines for the same data source, you probably have the task, maybe multiple tasks or one task sort of being customized to do those two transformations. Is that?
Not exactly. What we have ensured is that you get the file once and you do all processing in one shot.
Okay.
This is one thing which is super efficient. So since it's a batch
And it's a
process,
task based. It's a task
It is
based
task
which is
based,
hand
yes.
coded up
Yes.
for the requirement.
yes. We have written our own task manager. I myself done a particular task manager which actually says. And then there is a consensus manager to really say that if the file is processed once, and if you are uploading it many times, you really can say that okay, don't do it because it's waste of resources. Because in our production, what really happens is that since it is heavily multi-tenanted and these files, the chunks are generated anywhere from 5 minutes to 10 minutes to 15 minutes, you end up having lots and lots of files. So you need an efficient way to really process it, and simply wasting resources, I mean, by multiple processing is not correct. So this is somewhat a bigger picture. This is exactly the Spark embedded guy or the cluster which sits in, and then it is fed by the Spark, the task manager. Okay. So let me just show you a small demo. I mean, it's not a demo or something. It is just that on how to really use it. How we have really. So let me just go over the data first. This again. So the data looks something like this, where we have a timestamp, and we have something like what do you call it as this API, and let's go over the user agent, which is nothing but how someone has really browsed through a smartphone, a mobile browser, and a Safari, and stuff like that. And we have the metrics, which are nothing but the set of the response codes, the errors, and what is the request and response size that is there. So let me just say this is the input file, and let's say this is the schema that is extracted out of the input file. So we can just feed these two things and then get the aggregates done. So let me show you how to simply do it. Let me say that this is running in embedded mode. So basically there is an aggregate driver, and then you can simply say java minus jar and then just give the input file and the schema file. It will generate all the aggregates that is required in one shot. So let me just run it. It takes approximately 30 seconds, I think. So the beauty of Spark is that it can use all the cores that is required. Of course, I have 8 cores on my box. I'm just using 4, but in production, just in local mode, right? We just go and then use all the cores. Obviously, this doesn't come into picture when you are really using a distributed mode. You just launch it and just.
And that's what I want to understand. If we are using distributed mode, and I think he explained last, but I'm still not getting the idea. We have suppose maybe 5 or 10 nodes clusters.
Yes.
Then how we do parallelize using Spark? So I know writing as dot parallelize, but how it comes in, we still have to mention how many cores we want to run, or it's just by default whatever HDFS or this.
We can really mention the cores that is required, but the parallelization is done using min partitions that when you want to create the RDD.
If I don't want to specify myself,
It can do it on its own. It can look into the file sizes, it can do a lot of things. Basically, when you really go for the distributed mode, right, you always have a distributed FS, like HDFS or anything, and it has got its own splits, and using those splits, it can really.
so necessarily using all HDFS map reduce concept.
Yeah. So
it is
it's
only
the same
map
as
reduce. Even if you put a text file, it will be underneath using some of those calls to determine the splits and stuff like that. So that's why it's very great in using all the resources that's available. I have myself written a hash aggregate before writing that in Spark, where I had difficulties in reading a big file in splits, but Spark does it like this without any. And you can really control, and that is why I said in one of the learnings is that if you parallelize it very heavily, like if you split it like 32 times or something like that, then coalescing all the data, all the partitions and shuffle will be costlier. We just do it, max is something like 2x number of cores. Yes.
But because you're saying that, suppose there are data which is not running into hundreds of megs, it is running into megs.
Yes.
In those cases, would it make sense? To really split that?
Not exactly. You don't have to really split it. We have some small control where if it is not going beyond some X MBs, just don't. There is no need to split because all the load time can be simply loaded into memory and then just do a.
But do you use Spark in those cases?
We use Spark. Absolutely. That's the one of the use cases that it should be generic. We have some tenants which can produce data in KBs. Your tenants in MBs, it can some runs into GBs.
So pandas or some.
No, it's difficult to run such small tiny programs in production. We need a framework. If you have something like X number of deployments, each one varying, right? Then it becomes very, very difficult to maintain multiple frameworks. We need a general framework which can literally do efficiently for all of them. We have tried Hadoop, right? But it is not so good when the file sizes are really small because the startup cost is quite heavy, right?
So in your use cases,
yes.
Say you are multi-tenant, are you spawning are you running a common cluster or are you running separate cluster for each of the customers?
Common cluster. Just have common cluster. The idea is that there is a driver program that I showed, the driver nest I run, right? It is somewhat little modified to do some notifications and all that. And then once you have the driver program, you just input the file location, basically it's in S3, and then the schema. It can also derive the schema, and we have a separate data preparation phase where it can derive the schema and some of the fields and all that stuff. And then it can just run on it. So that's how, the other thing that I showed, the bigger picture of the architecture, that's, takes care of it. There is actually a data preparation phase where it actually prepares the data file which the Spark can, efficiently process. Because if you have something like 200 fields, you obviously don't need all the 200 fields to be loaded into memory and then all the things, right? So we have even a data preparation. We have partition control, where you can control what is the number of partitions that you really want to make. And that is all derived from experience once you really see and then start using it, right? You can really.
Because there will still be some distribution there. Let's say you take a KB of data.
Yes.
You're still going to make an RDD. Are you already?
Absolutely.
So you're going to make an RDD. That also has a cost.
Ultimately you have to have data in memory to really process it by.
It's just that it will not be RDD. That's what RDD will.
No. You cannot have multiple frameworks in processing data because it's a huge cost to maintain. Tomorrow, let's say we already have something like 7 running. We already have 3 coming this month. The number of aggregates, whatever you want, right? So let's say you have multiple platforms. Are you going to go and make changes in all the frameworks to accommodate this? And it keeps changing. And it's difficult to write it and write it correctly, to test it and all that. So instead you have a generic framework which suits everyone. Right? The best one is to do a hash aggregates, load everything into memory and do hash aggregates. I have myself written a small program before that and to validate whether the hash aggregates really work. That works only for KB. But the beauty of Spark is with RDD, the abstraction of RDD, right? You can literally manage KBs to GBs without you worrying anything. And with memory only, right? It works without any problems.
Do you run Mesos or a Yarn cluster?
No, no, this is standalone thing.
Standalone thing.
Standalone. Okay. We are not yet gone up to something like Mesos or something.
Okay.
We probably want to go to Yarn or something.
Okay.
And we want to use it more generically, I mean, for every other needs.
Okay.
So we may try Yarn. I am not very sure what we path.
Actually, you are using schema RDT, what are the
Sorry?
schema RDT or what are the
No, no, it is
aggregation
not
part you are
schema RDD. So we have not gone to the SQL of making SQL and then running SQL to get the aggregated data. We have written hand coded. That's what manual thing. So it's not a schema RDD. It is plain old RDD, which is loaded somewhat from text files or whatever the files.
But I think if data sources and the new schema RDD or the data frame use, I think this part will come in my critical business.
Yeah, lot of things. This is little old. This is like some December, even before December we had written. So then not sure we had something like that. So any questions? I am done. So let me just show you the results that would have come out. What we basically did was quite simple. Just launch the aggregated driver in local mode actually. There is not any distributed, giving the input file and the schema file, and then just say that Spark, you just go ahead. So these are some of the aggregations that it runs. Before that, it really sees if the aggregation fields are available for it, and then ultimately it puts all the results in a temporary directory. Of course, this is not what is in production. In the sense, after this, there is a result preparation stage where we collect all these things and then get the formatted output of it. So that's what. So this is how the the results really look like. And this is a raw results, and we want to get all the raw results merged and doing consume processing, and then load it back to the query store. Okay, that's the third phase in our architecture. So this is how it looks like. We were able to compute the percentiles very fast also. If you really see the API percentiles, this is very important because you're aware of the problems with percentiles, right? So the percentile computation is pretty tough because you would mostly need all the data in memory. And when the data set really runs into gigabytes, you have tons and tons of data sitting in memory. You would really want to have a smarter way of computing. You use digest to really compute. So yeah, that's all I had. These are some of the learnings that yes.
So before Spark,
Yes.
what we were using, or is it something new you already?
No. Before Spark, we had used to fire SQLs over our database. SQLs, literally SQLs, and it runs. The percentile query is like 2 pages, and it is the slowest one. It's difficult to come. And there are other problems like what happens if there is a lag. Let's say something crashed. There is a lag of 5 hours in computation of aggregation. Then it is little difficult to catch up because the database will be now overloaded with people querying the data and someone trying to compute the aggregation for the last 5 hours. Difficult to catch up. Since this guy computes, let's say you have a 5-minute interval, you can literally pack in as much as computing power you want and then just get all the aggregations done, because if you go to results, it hardly takes some seconds. That's all I had, the results and some of the learnings. So any questions? Okay, I think there are no questions.